Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabutewa Sos Ugobela Maths. And without any further ado, let's look at these questions that we have here. Okay, so we have question 5. It says, study the Maxwell-Boltzmann distribution curve for a certain reaction below, right? Then we are given that P and Q are the labels of the axis. What quantity is represented by P? Now we know that P here will have to represent the kinetic energy of the particles. So for P, we always have the kinetic energy of the particles, or sometimes they say of the molecules, same thing. So kinetic energy of the particles or the molecules. And then for Q, what we have in Q most of the time is the number of the particles, right? So number of particles. Okay. And then 5.2 says line R represents the minimum energy required for the reaction to take place. Write down the term of the underlined phrase. Now we know the meaning of that phrase is for the activation energy. So when we define activation energy, we normally say this is the minimum energy required for the reaction to take place. So that is activation energy. And then 5.2.2 is asking, how will the shaded area of the graph be affected when a catalyst is added? Choose from increase, decrease, or remain the same. Now, if we add a catalyst, we know that the impact that the catalyst has on the activation energy is that it decreases the activation energy, and by decreasing the activation energy, and then it allows more particles to have sufficient energy to collide, or it allows more particles to have energy that is greater than the activation energy. So of course, if we have to push back this activation energy here, then what we're going to end up having, because R here is representing the activation energy, if we push it back, what we're going to end up having is that the shaded area here will obviously have to increase, right? So our answer for 5.2.2 is increase. And then 5.3 says, use the collision theory to explain how a catalyst influences the rate of reaction. So now we are supposed to explain using the collision theory. So this is the collision theory for the effect of the addition of a catalyst. So this is how we go about it. We say adding a catalyst provides an alternative pathway of lower activation energy. So when we add a catalyst, we are decreasing the activation energy and therefore providing an alternative pathway for the chemical reaction. So adding a catalyst provides an alternative pathway of lower activation energy. Now this results in more particles. So more particles will have energy, will have a kinetic energy that is greater than the activation energy. So that is greater than the activation energy. So now if we have more particles having energy that is greater than the activation energy, obviously we expect this to lead to more effective collision, right? So leading to more effective collisions, leading to more effective collisions per unit time. So leading to more effective collisions per unit time. And then, of course, if we have more effective collisions per unit time, this will obviously have to increase the rate of reaction. Then we say thus increasing increasing the rate of reaction. That's how you're expected to explain that. So 4 points, 4 marks. Number 1, adding a catalyst provides an alternative pathway of lower activation energy, meaning more particles will have a kinetic energy that is greater than the activation energy, leading to more effective collisions per unit time and thus increasing the rate of reaction. Right. Then let's proceed. The reaction between powdered calcium carbonate, CaCO3, and excess hydrochloric acid, note the hydrochloric acid is in excess, is used to investigate reaction rate at 25 degrees Celsius. The balanced equation for the reaction is calcium carbonate plus hydrochloric acid 2, and then we have all that. Several experiments are conducted using the same mass of impure calcium carbonate and different initial concentrations of dilute hydrochloric acid. The graph below represents the result obtained. Assume that the impurities do not react, right? So if this is impure, we know that the impurities will have to be removed first because the impurities do not react. Now, they're saying 5.4.1, tell us what is the controlled variable. Right. Then what is the control variable in this investigation here? So obviously, since now they are looking at the concentration, we are told that this is used to investigate the reaction rate at 25 degrees Celsius. So that means that they maintained that the temperature will always be the same. Now, what is the control variable? This is the constant variable, the one that is always maintained to be the same. So for our 5.4.1, our control variable will have to be the temperature, because all this investigation here or all these experiments will be done under the same temperature, which is 25 degrees Celsius. So they are done under the room temperature. Then conclusion, what is our conclusion on this graph here? The conclusion, we can say the reaction rate is directly proportional to the concentration. As we can see here, when we increase in concentration, then also the average rate of production increases. What is this average rate of production? We are talking about the rate of reaction, right? So the conclusion in here is that the reaction rate is directly proportional to the concentration. So, or you can put it this way, and the reaction rate increases with an increase in concentration. That is also the same, right? Reaction rate is directly proportional to the concentration. Then for 5.4.3 now, let's here the space for that one. Then the calcium carbonate in 6 grams of impure sample, noted that the 6 grams is what? Impure. And then they said that assume that the impurities do not react. So number one, before we can calculate, we must remove the impurities because they cannot react. Then the calcium carbonate in 6 grams of the impure sample reacts completely with 0.03 mole dm cube, right? Remember, when they say it reacts completely, that means the pure sample of that calcium carbonate reacts completely, not necessarily the whole 6 grams that is impure. Then in 26 minutes. Then 5.4.3 says, use the information in the graph to calculate the percentage purity of the calcium carbonate. Assume that the molar gas volume at 25 degrees Celsius is 24,000 centimeter cube, right? So we can see that we are given that one there in terms of centimeter cube, right? Because even our average rate of production here is in centimeter cube. Now, the first thing that we obviously have to do here is try to figure out the change in volume for that. So we are given the rate of reaction, and then we are also given this. So we know rate of reaction can be written as the change in volume over delta time. We are given 26 minutes. So that means for our delta time, we're going to put 26 minutes. But then when this reaction is complete at let's check at 0.03. So they said it's 0.03. So that means it's not here, or it's where they indicated here. So at 0.03 mole dm cube hydrochloric acid, we can see that the volume or the average rate of production of the carbon dioxide is 50. So note that when the hydrochloric acid has a concentration of 0.03, the production of the carbon dioxide, remember the carbon dioxide is the gas, this is what we use to measure the rate of reaction. Right, so we're going to use that and say rate of reaction here, we have 50 centimeter cube per minute, and then we are looking for the change in the volume of the carbon dioxide. But then we do have our time here is 26. Now, if we can cross multiply to find our change in volume, we will say 50 multiplied by 26. That will give us our change in volume is 1,300 centimeter cube. Right. Remember, it is given in centimeter cube. Right. Now, we can use this one here to calculate. So now that we have the change in volume, we can start with our stoichiometric step, which is step number 1 is to obviously calculate the number of moles. So calculate number of moles. Now we have the change in volume, and then we know that the gas is always produced at STP. So that means the formula that we have to use is N is equals to V over Vm. And then we have our 1,300 divided by our Vm. We've been told to take our molar gas volume is 24,000. So we're going to substitute our 24,000 here. Then let's find our number of moles. When we divide that, it gives us 0.0542 mole, right? And then we know at this point, our step number 2, remember, what are we trying to calculate here? We are trying to calculate the percentage purity of the calcium carbonate. So this is what we are trying to reach here. But then step number 2, this is where we have to compare the ratio. Now we say, what is the ratio of carbon dioxide to that calcium carbonate? Find that the ratio of carbon dioxide to calcium carbonate is just 1:1. Now this means that the number of moles of carbon dioxide is also as well as 0.0542 mole, right? Because if they have the same ratio, that means they share the same number of moles, right? Now at this point, step number 3, we know from here, we have to calculate for the required value, which in this case, it is to calculate the percentage purity, right? Now, to calculate the percentage purity, we obviously need to calculate the mass, right? So how do we calculate the mass? So allow me to just write in here. To calculate the mass, we'll say we do have our number of moles is 0.0542, and then it's equals to M, which we don't know, but then the molar mass for calcium carbonate is 100, right? So allow me to correct here. Here I must say the number of moles of calcium carbonate, not of the carbon dioxide, because remember here, this was the number of moles of carbon dioxide. So now since the ratio is 1:1, the number of moles of calcium carbonate is still the same one. So, but then here we are saying the number of moles of calcium carbonate is 0.0542, which is the same as the number of moles of carbon dioxide. Now we want the mass of the calcium carbonate, so we use the molar mass of the calcium carbonate, which is 100. Then when we cross multiply this, that's 0.0542 multiplied by 100, which is going to give us 5.42 gram. Now, what is the meaning of this? This means from the 6 gram of impure sample, only 5.42 gram reacted completely, right? So from the 6 gram that we were given, only 5.42 gram reacted completely. Now, we know that the one that did not react would have to be the impurities. Remember, the 6 gram was impure. So the 5.42 gram is representing the mass of the calcium carbonate that is actually pure. Now, if you want to get the percentage purity, This is now obvious. We'll say the mass of the pure over the mass of the impure. So you still remember from our grade 11 stoichiometry, if we want to calculate the percentage purity, the formula was that percentage purity is mass of pure over the mass of the impure, and then you multiply that by 100. Now, what is the mass of the pure? It's the 5.42. And then what is the mass of the impure? Remember, the impure is the 100% sample. It's all of the sample, right? Then this is 6 grams, then multiplied by 100. Now, 5.42 divided by 6 multiplied by 100, we find that the percentage purity is 90.33%, right? So that means the mass of the calcium carbonate that is actually pure from that impure sample is 90.33%, and the rest is impure, which is making up about 9.77%, which is the impurities, right? So, but then the pure sample is 90.33%. That's how you were just supposed to go about answering this question. So please press the thumbs up button if you've enjoyed the lesson and then you found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.